Hi everyone, I'm Anish and welcome to PrepFusion. So today we will be starting the lecture 2 of this next chapter, right? Chapter 2, that is the block diagram and signal flow graph. So in this lecture we'll study what is a signal flow graph and the rules for using the signal flow graph, right? And questions using the signal flow graph. But before starting the SFG, right, we will do the question that I gave you for homework. So what was that question? Yeah, this was the question, right? So here the block diagram of a system is shown in the figure, and like this is the block diagram. We have to find the transfer function, right? So what we'll do is, like, I hope you have done the homework. So let's cross verify how you did it, right? So first method that I will use is using the block reduction technique, and second method is simply using the equations, right? So method 1, block reduction technique. Okay, so what I will do, I will copy this here, so you may have to draw it over and over again. For me it's simpler, so I will copy this over here. Now I will see, like, how can I simplify this block, right? So what I am observing is these two, right? These two are in parallel in some sense, but here is the problem. Here I am taking output, so I just simply can't add them, right? So if I somehow move this here or here, then it will be easier for me than to reduce this parallel combination, right? So after the adder is moving this after the adder is a bit complicated. So what I will do, I have a gain block here, I will try to move this here, right? So what I can do is, now how like if I move this before the takeoff point, before the gain block, then what changes do I have to make? So first let me observe. Let's say I have a signal x over here, it becomes x times g2 right here, and here it becomes xh times g2. So if I move this signal from here to here, so the output of this block, right, should remain xh times g2. So now if I move this from here, so I have x signal here, it gets multiplied with h and I get x times h, but I don't have g2, so I need an extra gain of g2 here, right? So what I will do, I will put an extra gain block of g2 here, okay, in cascade, and that will be simply like the overall gain block will be h times g2. Okay, so let me make this a bit smaller. Paste this. So what I will do, I will remove the, I will take this point, okay, it is too big, take this point from here to this end, right, to this end, okay, this end, and so this is x, so I need xg2 here, so I will add a gain block here of g2, right? So this will simply be replaced with h times g2. Okay, this will be simply replaced with h times g2. Now adding these two, right, is simpler for me. Adding of these two is simpler for me, so I will reduce these two into a single block of g1 g3 plus g2. So I will just simply delete this and add these two, right? So it's easier for me. You have to again draw a new block. Okay, so I will just delete this one. Remove the adder over here. So adder will be removed because simply I'm adding these two, right? So adder will be removed, and this equivalent becomes g1 plus g3. Okay, and we're taking the output from here. Now what I can observe here is this becomes simple addition. Okay, now what I have to do is, like here, right, I have to again reduce this further. So how will I reduce this? Now what I can do is again move this point to here, okay, so that I can replace this whole combination to a negative unity feedback, right? Because this is looking like a negative unity feedback. Now moving this point to here, will be a bit complicated because we have adder. So generally I tend to not like go to the adder path. Instead I tend to go to the gain block path, right? So I will try to move this again to here, so that what happens, that this combination becomes a negative unity feedback, and I can replace this feedback with one single block. Okay, so now again, like copying this, now what I am doing is moving the takeoff point after a gain block. What will happen now? The gain will be divided this time. The gain is G2 plus G3. It will be divided this time. Previously it got multiplied because we are moving it before a gain block. Okay, so self-explanatory. Still, if you can't understand, I will again solve you from basics here. So okay, so let me move in here. So what will happen is simply what is the signal here? We have xh times G2, right? So again, if I move this to here, what signal do I have at this point? I have x times G2 plus G3. I have G2 plus G3. Now if I take that signal from here, then extra gain of G2 plus G3 will come up. So I need to divide by G2 plus G3 so that that gain term gets cancelled out. So what I will do is replace this. Okay, copy and paste this over here again. Delete this. And take from here itself. I can take from here also. Okay, for like better visualization, I will take from here also. Okay, so what does this become? So now if I have extra G2 plus G3 gain over here, so I need to divide this block, right? Need to divide this block. G2 plus G3. Okay, G2 plus G3. So this is the like the block will replace like this. Okay, if I move the takeoff point after a gain block. So yeah, I hope you're understanding. Now what I will do, I will replace this whole combination with a single combination. What will be the value of that single gain block? So it is G upon 1 plus GH. So G2 plus G3 divided by 1 plus G2 plus G3. Okay, so this whole combination, right, will be replaced by this single block. Now what will happen? Now this combination, right, whole single block will come in cascade with this G1. So what will be the overall like gain of the single block? Then if these two are in cascade, it will be simply G1 times G2 plus G3, right? Okay, let me like draw that so that you will be able to understand. I'm doing this slowly, but you can do it like in examination. Obviously you have to do it a bit faster. Okay, so I will replace this. This will be replaced with a single block basically. Okay, this will be G1 times G2 plus G3 divided by 1 plus G2 plus G3. Okay, so this is simply the single gain block. Now what I can do is simply again convert this is a negative unity feedback. Again I can convert this into a single block, right? So what will be the conversion be? So it okay, let me calculate this. So simply now I can directly write the equation, right? CS by R of S equals to simply, now we have this denominator, right? I will just write the numerator G2 plus G3 into 1 plus G2 plus G3 plus G1 G2 plus G3 into H G2 divided by, we have also like here also we have G2 plus G3, right, in division. So G2 plus g3 is also here in division, right? So like now how will I do it? So simply again like taking the common, multiplying g2 by g3, g2 plus g3 in both sides. Okay, sorry, this g2 by g3 anyway cancels out, right? So we have g2 by g3 in the numerator also. Okay, that was the confusion that I was getting. So this g2 plus g3 anyways cancels out. So what is the transfer function? Answer we get as is g1 into g2 plus g3, then we have 1 plus g2 plus g3, then we have g1 into h, g1 g2 into h, g1 g2 into h. Okay, so this will be our answer for the question. Now let's cross verify it with the second method, right? Okay, so method 2, using equations. Okay, so what let me take the block diagram again. So this was the block diagram, right? Let me take and put it over here. So what I can do is I can like assume C here. So C point is here, right? So what I can do, C assume here. Okay, I'm assuming C here. Okay, now this what does this become? I don't know. What does this become? I don't know. So I have to assume some unknown point again. So what I will do is assume x over here. Okay, this x gets multiplied with this h, and we get x into h over here. Let me take another color. Now here we are subtracting r from, like we are subtracting xh from r. So this becomes r minus xh. So what does this become? This becomes r minus xh times g1. Okay, now what does this become? So again we are subtracting c from this one, right? So I'm not writing s over here, because s we can, I mean for now we can, obviously we know that it is a function of frequency, but for now, for all these calculations, right, we will always not write s, else it will become very messy. So this is already becoming very messy. I will not write it. So what is this this point, right? This point is x by g2, right? This point is x by g2. Simply dividing the gain block, right? Dividing the gain block. This is just mathematically possible, but actually we can't go into representation, which we'll learn in the SFG. So x by g2. So again, like now what I can do is simply do one thing. This is x by g2. Now we multiply with this g3, right? So what do you get? X g3 by g2. Now we are adding x and x g3 by g2, and we get, what do we get? We get c. So I can write the relation between x and c from this node, and at this node, right, I can again get another relation between r, x and c, and from that I can replace x to this relation, and I will get my desired answer. So yeah, first let me write this relation between x and c. So x, okay, let me make the pen a bit thicker. X g3 by g2 plus x is equal to c, right? Equals to c. So what is x equals to? X equals to g2 divided by g3 plus g2 times c. So I will replace x in the next equation from here, right? So what is the next equation? So next equation is this one, right? So at this node, what is happening? R minus xh minus c is x by g2. So r minus xh times g1 minus c equals to x by g2, right? So this is the node equation at that point. So what I can do is simplify this. So getting x as common term, right? So r g1 g2 minus x h g1 g2 minus c g2 equals to x. So r g1 g2 minus c g2 equals to x1 plus h g1 g2. Okay, so now what I will do is replace x by c, right? So what is c? I mean what is x? G2 by g3 plus g2 into c. So r g1 g2 minus c g2. Okay, just don't ignore my g, right? These are also g, so try to understand that also. So this is g2 divided by g2 plus g3 times c into 1 plus h g1 g2. Okay, yeah, this one is it. So now I will take this c to that side again. So r g1 g2 equals to, taking c common. Okay, taking c common, what do you get? G2 divided by g2 plus g3 is one term, right? So okay, g2 divided by g3 plus g3, I can take it here also. Okay, this is also now h g1 g2 divided by g2 plus g3. Okay, that is the main like drawback of this particular like method, right? So you have a lot of calculation to do. Okay, this becomes g2 square. Okay, g2 I can take out, right? Common, g2 I can take common. Okay, so simply what I can do, g2 take common, so don't need to worry about g2 anymore. Okay, so here, okay, this g2 is gone, this h g1 g2 is there only, so g3 plus g2. Now this goes there only, we have to add 1, right? See, I take common, we have to add only 1 plus 1. Okay, this g2. So now this is r g1 equals to c g2 plus these coefficients are common only, this is g1 plus g2 and this is g2 plus g3 divided by g2 plus g3. Okay, something I have done wrong actually, something I have done wrong here. What I have done wrong? Okay, let me check and then come back actually. Okay, this g2 is, yeah, this becomes only 1, right? This becomes only 1. Here we don't have g2 on anymore, we have only 1. Okay, this is 1. So now like we can simplify the ratio, c by r, right? C of s by r of s equals to, this becomes g1 into g2 plus g3 divided by 1 plus g2 plus g3 plus h. Okay, again this is not plus, this is actually multiplied. Sorry for the like calculation. I have like, if you do it by yourself, you will understand. I have to like think and write also, that is difficult. So yeah, so this is the transfer function that we get with from this method, right? So as you can see, yeah, both of them are same only. From here, this is also same and this is also same. So you can like cross verify, or like now whichever you find suitable, you use that, right? So yeah, this was one thing to keep in mind. Now let's start our lecture for this like main topic of this lecture, right? Signal flow graph. So like firstly, what is a signal flow graph? So signal flow graph is a graphical representation of block diagram system. Okay, SFG is used to determine the like what do you mean by graphical representation? First, let me come back to that first. Basically, we have one block diagram, right? So if I can graphically represent it in terms of wires and things, it becomes easier to draw, and how we analyze it we'll understand, okay, in this lecture. So what is signal flow graph? You understand, it is a graphical representation of the block diagram basically. Okay, we represent with graphically. How I will show you in the next few slides. So SFG is used to determine the transfer function between any two nodes. Now what is node? That also I will explain, but it is mainly used to find the transfer function between any two nodes, not only between the input or output, between any two nodes, right? For a given input and for a given output, we can find the transfer function between those two nodes only. Okay, for any given input and any given output, between those two nodes we can find the transfer function. Okay, now SFG is an easier way to determine the transfer function compared to block reduction technique. Yeah, it is easier because there is like just a certain set of rules and formula that you have to use. But like when we use SFG is that whenever like what I used to do was, whenever I see like I have already told you, I think, that block diagram has very high number of adders, then what I will do is I will use this only. Okay, because SFG is easier with adders. With adders it becomes very complicated for block diagram reduction, and also with equations also it becomes difficult, right? Because as you just saw in the previous example that it was getting lengthy and I could have made a calculation mistake. Okay, so yeah, SFG is better in that perspective, right? So also SFG, this is just for knowledge purpose, this is not that important, just for knowledge purpose. SFG is based on distribution parameter where gain is distributed across the line. Like we have a line, right? So gain is distributed across its whole line. Now like between the two nodes, whereas block diagram is based on lumped parameters where gain exists at a point. So here it is based on lump parameters, so gain exists at this point only. Okay, gain exists at this point only. This is just for knowledge purpose, not that important. Now one thing to note is that SFG applies only to linear systems. So we can apply SFG only to linear systems. So if we have been given two inputs, right, two inputs, we can find the transfer function for one of the input with the other input turned off. Then we can find the transfer function of the other input with that first input turned off, and we can simply add those two. Okay, we will get our overall transfer function. Okay, so that's why this is only valid for linear systems. Now this will follow the property of linearity. The equation for which SFG is drawn must be algebraic equations in the form of cause and effect. I will explain you what do you mean by equations, but when we write the equations, right, they should be in the form of algebraic equations, and they should follow the cause and effect. What is cause and effect, that also I will explain. Just read these points, right? Read these points. Now nodes are used to represent variables. I will also explain like what are variables. Normally the nodes are arranged from left to right. So normally our flow, what will be our flow is, we'll go from here to here, right? In block diagram also that is our flow. We have one R here, then we have one C here, and like we're going from left to right, right? So in SFG also our flow is from left to right. Okay, also like this signals, right, this like from input output following a succession of cause and effect relations through the system. Okay, they will follow a cause and effect relations through the systems. Now signals travel along branches only in the direction described by the arrows of the branches, right? What do you mean by that? Is that there is a signal, right? In block diagram, how do you show the signal flow? Like this, arrows, right? But in signal flow graph, how will I show? I will show like this. Okay, the arrow will be like this, so signal will flow from here to here. Okay, so I will again like take one example and explain it to you. But first, what important point is that these things, just to get your notes ready, this is the important. All things I will explain in the next few slides. Okay, with example. Just listen to what I am saying right now. Like in SFG, we determine the cause of action, that is the transfer function, by using Mason's gain formula. So this is the Mason's gain formula. So one by one I will explain you what does each term mean. Okay, so this Mason's gain formula is C by R equals to summation of k equals to 1 to n pk delta k by delta. So what does this mean? So this C, right, C is our output node, the node from where we are taking the output from, and R is our input node, the node where we are giving the input to, and this is summation, not that like we don't need to explain it. Now what is P, right? P is the forward path gain, and delta k is the associated loop gain with that forward path gain. Like don't need to understand the terms, just what I am saying, just listen. And this is the loop gain, determinant of the signal flow graph. Okay, and what is n? N is the number of forward paths. N is the number of forward paths. Okay, n is the number of forward paths. So what I will explain every term is bit by bit. So first let me explain what does input means, right? What does input mean? So input means, let me write it. Input means the node which has only outgoing branch present from it. So all the branch will go out from it, right? None of it will go in. Okay, that is node outgoing branch which is only present, right? So what will be that? So basically, right, let me take an example. So let's say this is R of S. So only nodes will branches will glow out. So these are known as branches, right? The path between two nodes are known as branches. Okay, so these are known as branches between two nodes, and only signal will flow out from that node. Now what does output node mean? So this is the input node. What does output node mean? So node which has only incoming branch present. Okay, let me copy this, like no to write this again. Node which has only incoming branch present. Okay, so what do I mean by that? So I have C of S here, right? C of S here. Okay, so this will be called our output node, because only every branch, right, is incoming to that node. None of it is outgoing from that. Okay, but one important point to note is that, side note to note is that a non-output node can be converted to a simply output node just by making a simple modification. A non-output node can be converted into a output node by simply making a modification, simple modification. Okay, I will not write simply here, just that non-output node can be converted into output node. How? So let us take a example of signal flow graph. So I will take one example. Okay, so this is that. Now we have an M, N, and okay. So these are just nodes. Okay, M and all of these are nodes. This is the input node. Okay, R of S. Our flow is from left to right. C of S, and these are I name the nodes. Whatever you want to name, you can name. You can name A, B, C, D, whatever you like. Okay, I name that as whatever I felt like. So this is M and O. Okay, and we have another signal flow from here to here. Okay, so these are the flow directions. Okay, these are the flow direction, and for now, let's say these are the gains only. So the gain is only one. Gain will change. I will explain you what is the gain of that path in later examples. For now gain is only 1, let's assume. So what I can say is all the branch is flowing out. The nodes the flow between those path between those two nodes are known as branches. So through this, right, to this, all of them are outgoing, okay, and at this node all of them are incoming. Only one is present, so one is incoming. Now can I make this node, right, the node O, can I make this node output node? Make node O output node. How will I make it? What I will do is simply take one branch out of this, okay, simply take one branch out of this and mark that as output node, or a simple another node, right? So what I will do, copy this, I take a node out from here. So this is the output node and this is 1. So let me name this differently. Let me name this as O dash, okay. So this O dash will be our output node, okay, and this will not affect the overall system. Overall system won't be disturbed. Why? Because we're simply taking an output from here, we're not giving anything. So taking something, it doesn't cause any loading effect in our control system, this whole the whole subject, right? So it won't cause any disturbance, okay, to the system. If I just simply take an output of gain 1 from here, so this will be converted into a output node. So output node, okay. So now what is the another point to note is that a non-input node cannot be converted into a input node. So this is an important point. Okay, let me copy this only. Oh no, not cut. Okay, let me write it only. Non-input node cannot be converted into input node, right? Why? Because it will affect the overall system, right? It will affect the overall system. Let me explain. So again, take the previous example, okay, take the previous example, this one, right? So in this example, now let's say instead of this node being output, let me make this node as input. So we'll give one input over here, okay, gain is 1, but here is some input like rs dash. So what will happen now? This will affect the system because this is also giving some input over to this output and this is also giving some input over to this output. So the actual ratio, right, ratio of C by R will change, okay, the ratio of C by R will change, okay. So this will affect the system gain will change, this will affect the system. So we cannot convert a non-input node into a input node, but output node, it won't affect the gain of this overall system, it won't affect the ratio of C by R, right? So yeah, this is the overall system, right? This is the overall thing that I wanted to mention, few key points, okay. Now let's come back to the formula, right? Explain that we have explained this input and output node. Now we'll explain this formula. So pk, what is the pk? What is p? Basically p is the forward path, okay, or we can say forward path gain. Pk is the forward path gain. Now what is forward path? So let's first understand what is forward path. What is forward path? So it is the path from input node to output node without any repetition of any of those nodes, okay. It is the path path from input node to output node without any repetition of these nodes. Okay, so yeah, this is what forward path means. So what do I mean by this? So we have this input and output, right? Input and output. I want to go from input to output between these paths, right? So how many paths do I have? Okay, but there shouldn't be any repetition. We will also get a repetition. From there we will understand that like which is a forward path and which isn't a forward path. Okay, so here I can see I have one path, okay, and there isn't any repetition. That what path do we follow? We go from R to M to N to O and then C. Okay, one path. Then we have another path, this, right, this one. So we are going from R to M directly to O and then to C. Okay, so we have two forward paths for this particular example. Okay, so this is basically the forward path, that is like just the path. What does forward path mean? That I explained to you. Now what does PK mean? What does PK mean? PK, right? PK means the forward path gain. Okay, PK means the forward path gain of that particular path. Okay, here this is the kth path. Okay, but I have your understanding, it is the forward path gain of that path, of the particular path. So here, right, what is the overall gain of this path? It is like here all of the gains are 1 only, so it will be 1. Okay, and from here also the gain is 1, that is 1 times 1 times 1. Okay, and here 1 times 1 times 1 times 1, that is the gain of each branches, right? The gain of each branches get multiplied, okay, to get the overall gain of the forward path. Okay, it's like they are connected in cascade. So yeah, that is the PK, right? Forward path gain. Now what is this delta K? What do we call this delta K? So delta K is known as the associated path factor. Okay, it depends on the forward path and isolated loop gain. What do I mean by isolated loop gain? Let's see, but first let me write PK, delta K. Delta K is known as the it is known as the associated path factor. And what does it depend on? It depends on the forward path and isolated loop gain. Depends on isolated loop gain. Okay, so now I will come back to isolated loop gain, but first let me define this term, right? What is this delta term without any suffix K? So this delta, right, delta is known as the determinant of the SFG. Okay, determinant of the SFG. So like what is the formula for delta? So delta, right, delta can be expanded in this form. Okay, just don't get frightened by this form. Okay, this is very simple only. At first glance this may look like what is this form and what is this difficult form, right? So delta can be expanded like 1 minus summation of individual loop gain. Okay, summation of individual loop gain plus summation of product of two non-touching loop gains. Like you may ask, what do you mean by non-touching and what do you mean by two product, like what do you mean by that? This I will explain you with example. Okay, then again we go to minus summation of product of three non-touching loop gains. Okay, and this will go on non-touching loop gains. Okay, and this will go on, right? This will go on. One thing you have to keep in mind is, if like this term is 0, then the terms after all this will also be 0, because if there are if there aren't any 3 non-touching loop gains, then there won't be any 4 non-touching loops, right? If there aren't any 3 non-touching loops, there won't be any 4 non-touching loops. What do you mean by this? We'll do example and there you will understand. But just keep in mind, if there are 2 non-touching loops, we have 2 loops, right? And they are touching each other, and overall SFG we have 2 loops only. What do you mean loops also? I will explain. We have 2 loops only. So what will happen? There can't be 3 non-touching loops, because we have only 2 loops and 2 loops are touching each other, so it is impossible. So if one term is 0, the terms after that, right, will also be 0. Okay, so this is an important thing to notice that. And another important point to note is that if we equate this determinant delta equals to 0, then this equation, right, equation is known as the characteristics equation of the system. Okay, characteristics equation of the whole system. Okay, so this is basically what delta is. Now delta k, right, that I explained earlier, associated path gain factor, is also similar to this. Just the difference is it will be isolated. So let me just copy this one. Instead of individual loop gains, it will be isolated, individual isolated loop gains. What do I mean by isolated? Isolated means if I remove the forward path for that particular path that I am searching for, right? If I remove that forward path, then how many loops are present after removing the forward path? Okay, so that is what we mean by isolated. We will do example and there we will understand. Okay, so what? Okay, I will just simply add the extra term is isolated. Okay, so isolated means they are not touching the forward path. For that particular forward path, that loop is not touching the forward path. So that is what an isolated like loop gain means. So okay, isolated. Let me bring this down. Path loop gain. Okay, and this is this second term will become non-touching isolated loop gains, right? Isolated loop gains. So this is only isolated only. I can bring this over here. Non-touching. This will be here. This is isolated. Okay. Product of 3 non-touching. And this will go on. Okay, so isolated, what do you mean by isolated? It is not touching the forward path for that particular, right, for that particular forward path. So we have here, we don't have any loops here. If I had a loop, I would have explained you, but this is the forward path, right? So if I remove this forward path, then how many loops are present? Okay, after removing this particular forward path, now we have this another forward path. If I remove this forward path, then how many loops are present? Okay, that will be the associated path factor for that particular forward path, right? So yeah, this is basically it for the whole equation. Okay, so from block diagram, how do you convert? We make flow equations. So again, I have already told you, but I will just explain it to you a bit. Okay, that we make what do you mean by flow, right? So we make a line. Okay, then this is the direction of the arrow is known as the flow. It is going from left to right. Okay, so flow is like an arrow. Flow is shown like an arrow. but one thing to remember is we can't go in the reverse direction. Okay, so reverse direction we can only go with the flow, okay, so we can only go with the direction of the flow. Okay, so that is one important point to note here. Okay, so this was just an explanation. And another important point is, like, let's say I have one gain block, right? G of s. I have a gain block G of s. How will I write this in signal flow graph? So I will have, like, this is, let's say this is R of s and this is Y of s. This is the gain block G of s. This is the gain block G of s. So this is the flow equation. Okay, so this is how I can convert this gain block into a flow diagram, right? So now what can I do? Simply, one thing to note here is that mathematically, right, what I can write mathematically is Y of s is equals to G of s times R of s, right? Now mathematically I can write this, that this R of s can be written as Y of s by this G of s. This is mathematically correct. But this is not equivalent, right? Because we can't, like, I forgot to put a direction over here, we can't go against the direction, right? We can't go in the reverse direction. We can only go from R to Y. We can't go in the reverse direction. So reverse direction is we can't go actually. Okay, so this is mathematically correct, but this is, like, in reality this is we can't define this. We can say it like this. We can only go from input to output. So our flow direction will be like this only. Okay, so yeah, this is one important point to note, is that, like, in which direction the arrow is, that is the direction of our flow. Now how to make flow equations, how to write flow equations, let me explain. So let's say, let me put the heading over here. So let's say I have like multiple paths here. Okay. This is one path, this is one path, this is one path. Okay, this is 1 2 3. Okay, now we have, like, say 4 paths, right? And these are all of them are, let's say, inputs. Okay, R2, R3, R4, and each path has gain G1, G2, G3 and G4. And what is this node called? This node is called Y. So what is Y equals to? So Y equals to, simply writing the algebraic equation. So from this node it is coming as R1 times G1 plus R2 times G2 plus R3 times G3 plus R4 times G4. Okay, so this is the flow equation. Okay, but one thing to note here is that I can't go from Y to R1. I can't do that. I can go against the flow. Okay, I can go from R1 to Y only. Okay, so yeah, this was the important point to note. Now what we'll do is do few important rules of signal flow graph. So if we have a summing point, okay, how can I replace the summing point? So let me write the heading here as summing point. So how can I replace the summing point as? So what I can do is simply replace the summing point with a node. Okay, replacing the summing point with a node, and this is the output node, and here something is incoming, right? The node of the like gain of this branch is G of s, and gain of this branch is H of s, But one important point to note here is that it is going in negative, right? So how will I show the negative branch? Will I reverse this flow? No, the flow direction will remain same. What I will do is I will change the sign of h of s with minus h of s, so it will become minus h of s. Okay, so here when any input signal is coming and this is outgoing, okay, this is outgoing and this is incoming, okay, minus h of s. So yeah, this is what our flow is. Okay, this is what our flow is. So this was one of the rule. Okay, now another rule is basically takeoff point just after the summing point. How will I represent it in flow diagram? So again, after and how will I represent it? So what I will do is simply like this is input and output. So this we have already understood. I will again assume an extra node over here, okay, an extra node over here, and take the output from there. Okay, so okay, let me minimize this a bit. Sorry. So we have a node for the adder over here, and I will use another node for the takeoff point, and from this point I will take the different like branches, right? And we have one node like branch coming over here whose gain is minus h2 times s. This is g of s, and this node, right, this what I will assume the branch, the gain of this branch, what I will assume this one, okay, because this is one only, right? This point is same only. But just to be like on the safer side, because this may cause you few calculation mistakes, how we will understanding while solving questions, and in the we can combine this into a single node also, that I will also show. Okay, but if I am taking it as different nodes, what I will do is assume the gain as 1. So what is the gain of this? This is h1 of s, this is g of s, right, and this is h2 of s. Okay, so this is what our call, this is what we call. Okay, so this is how we can convert it. What we can do is we can also combine the whole combination, right, into one node, because this point and this point is same only. But this may cause a calculation mistake if we have bigger diagram and more complex diagram. Okay, but I will show you how can we combine this into a single node, because both of those points are same only. So what I can do, simply this is the input, right? So what I can do is combine them here, take the output from here. Okay, let me draw all this because you might not understand. This is just another system that is coming from. Okay, I'm not drawing the whole signal flow graph right now. So this is h1 of s, this is g of s, and we have like from another system we have another incoming. Okay, minus h2 of s. So this is like how we can convert this into a single node, right? But this is a bit risky, so what I will recommend is generally show them as different nodes. Okay, that will not cause you any mistake in the exam or in getting the final answer. So combining the nodes. Okay, so yeah, now another example is if the takeoff point is before the adder. So for this case it's easier only, you have to consider different nodes only. Why? Because the point, this point and this point are different. okay. This point and this point are different, because here after this subtractor, right, we're getting this, okay. So this point is of different value and this point is of different value, so we'll consider two nodes. One thing to note is that, so this is not adder, actually this is a subtractor. So what I can write here is subtractor, just a terminology. I hope like you already understood that. Summing point, you can say it summing point or subtractor, whatever you want to call. Okay, so again, like takeoff point is just before, so let me copy this only. Here we'll assume separate nodes. Okay, here we'll assume separate nodes. So like how we can't merge, we can simply merge the whole three nodes, right? So what I will do is, again, make this a bit smaller. So what will this become? Assume this as different node and this subtractor as different. Now this is going to different block. Minus h2, this is a different, okay. No, this is not going here, this is not the summer, this is just the takeoff point, right? So this, right, will go here only, okay. Geos. So this is how, like I will combine if the adder is just before, okay. So yeah, this is how I will write this. What will be this gain? This gain will be 1, okay, because I'm going from here to here. This gain will be 1, okay, but I can combine this because at this point the value is different, okay. At this point the value is different, so understand that. So always, to be on the safer side, always make them separate nodes, okay, just to be on the safer side. So I've already told you if there are multiple summing points, right? So like if there are multiple summing points, let me give you another example. Just connect them in parallel, right? So let's say like this signal is coming, okay, and this signal is coming. This is each one of us, and this is h2s, okay. So how can I represent? This is minus minus and this is plus only, okay. How can I represent this? So this is one system again, and the system, like system, or you can say the there are some like things on that side. So how can I replace this? Simply create a node over here, okay, and what I can do is, like here I have some output, okay, here I have some output again to this block. I'm not writing it, so this is some output, just add them, right? Just add them over here, okay. What will the gain of this one? It will be minus h1, it will be minus h2 of s, h2 of s, okay. So this will be the gain block basically. So yeah, this will be when multiple summing points are connected in parallel. This is for okay. So this is what like how few basic rules for like the SFG, right? So next I will do one example problem for the SFG, and here you will understand the concept of how to use the SFG. So this is the sixth problem, let's say, and this is very basic problem, okay. So what is the basic problem? Basically the negative feedback one, okay. So we'll draw the negative feedback here. This is, and it's like, let's not do it unity anymore, let's do it as some gain g, some gain h, right? So this is simply c, this is simply r, let's say, and this is subtraction, this is addition, and we have gain of h over here, and we have gain of g over here. Okay, so we already know the result for this one. Okay, so we already know the result for this one, but we will calculate this using SFG. So this adder, we can replace this with node. This is a takeoff point, we can replace this with a node. Okay, and this is the direction of the arrow here. Okay, so let me draw the SFG. So well, let me write the question: find C by R using SFG. Okay, find C by R using SFG. So what I will do, I will replace this with a node, So how many nodes I have? This input and output node plus 2 nodes, so 4 nodes. So let me draw a straight line like this: 1, 2. This is the input node, this is R, this is C. I will name this node as M and N. So there is connection between this node M and N, right? So what is that connection? So the connection is simply this one, right? So M is getting connected to here, so there will be some feedback from M to N. Okay, and what will the gain of that? It will be minus H, because there is a negative sign here. So taking into effect of minus sign with here, the flow is in this direction only, because here where we have the flow, right? So flow will be on this direction only, but it will be minus H. And this is what is the gain of this branch? It is G only. What is the gain of this one? 1 only, because from here to here there isn't any change. Okay, so 1 only. From here to here also there isn't any change, so this will be also 1. Okay, this will be also 1. Okay, so this is simply input node, this one is input node, and this one is output node. So from here we'll find the transfer function, right? C by R ratio. So first I need to find how many number of forward paths are there. Number of forward paths, number of, first few I will do very slowly, but next we'll write directly. You will see how fast we can do. Okay, it may seem at starting that yeah, this is a very lengthy and slow process, but once you get the gist of it, hang of it, it will be very fast for you. Number of forward path equals to 1. How? Only this one, right? From input to output without repetition of any node, we can go from here. Yes, you might ask, yeah, but I can do like this, right? I can go from this, right? But what is the issue? This M is getting repeated twice. Once I am crossing this M, I cannot cross it again, so I can't go like this. Okay, I can only go like this one. So from here, I hope you're understanding what does that repetition means. Okay, so what is the forward path? It is R, M, N and C. Okay, R, M, N and C. So like what is the C by R? Let's write the C by R. Okay, this time C by R is the summation of k equals to 1 to n. Did I write k equals to 1 over in that formula actually? Yeah, k equals to 1 to n. Okay, so this is actually n, this is actually n. K equals to 1 to n. Okay, this is pk delta k by delta. Okay, so this is like, how can I replace it? So we have only one forward path, so we don't need to sum anything. So we'll have only one value, that is p1 delta 1 by delta. Delta remains same anyways. Now what is the forward path gain? That is p1. Step 2 is finding the forward path gain P1. So what is it? Here what I can observe is I'm going from here to here, right? So what are the gain blocks that I see? So I see 1, okay, done. Then from M to N I see G, so 1 times G. Then from N to C, what do I see? I see 1. So 1 times G times 1, okay, that will be my forward path gain. So what gain I am seeing from going from input node to output node? So it is 1 times G times 1, okay. So this P1 becomes G, okay. Now what is the step 3? Step 3 is the associated loop factor, right, with respect to this forward path. So but before that I will find the determinant, okay, the determinant of the whole SFG, right? So step 3, what will be delta? So delta will be 1 minus individual loop gains. So how many number of loops are here? So what do you mean by loops? Which come back to its previous path, right? Which come back to its previous path. So one node, at least one node is repeating without any other node repeating. At least one node should repeat. That is what a loop is. So I understand loop anyway. So in current KCL equations we do loops also there, KVL, all those things, okay. But here also we can see what is the loop. Loop is M, N and M, okay, that is repeating. So M, the node is repeating once. We're coming back to the same node again. We're coming back to the same node again from where we started. That is what basically loop means, right? So number of loops is 1 in US. So what is the individual loop? How many number of individual loops are there? Only 1. And what is the path for that loop? It is M, N and M. We're going from M to N to M, okay. And like it is only one loop only, okay, one loop only, so it doesn't matter. So we won't have any two product of two loops, like in the second term, right? We won't have this term because we have only one loop. We will also understand like when this term come into action, right? This term won't come into action, only this okay, missed one thing. I should write here delta k. Actually this is a mistake from my end. This is delta k, okay. Okay, this is delta only. So only this term will come into action, all these terms will be ignored, okay. So what is the loop gain? I can represent the loop as like this and the path of that particular loop like this, okay. This is just my convention, okay. You don't have to do all this, you can write it directly also. I will write this directly in the next few examples, okay. So here what is the loop gain? So I'm going from this path and coming to this path. What gains do I see? I see G, then I see minus H. So G times minus H, which is minus GH. So minus GH, right? What will be our delta? So delta will be 1 minus L loop gain. So it's the first term only. So 1 minus GH, which is 1 plus GH equals to, so this is our determinant for the particular SFG, okay. Just important thing to note here is you should not change any signs or direction. So what you want to do is change the flow direction and change the sign also. No, you can't do it in a SFG, okay. So it may be mathematically correct, but like it will cause error in the calculations, okay. So don't do that. So now let's find the associated loop path factor. So this was a step 3. Now let's do the step 4. Associated path factor. So what do we mean by this is the loops should not touch the forward path. So loops should not touch forward path, right? So while calculating the associated path, what I will do, will copy this, right? I will remove the forward path and see how many loops are present. Okay, this is what I do generally. So what I will do is just delete this forward path, right? Delete this, and along with this the nodes will also get deleted. Okay, the nodes also will get deleted. So do I have any loop remained? This was the loop, but this node got deleted and this branch also got deleted, so I don't have any loops remained. So if I don't have any loops, so the loop gains will be 0. So no isolated loops present, hence loop gains will be 0. So what will be my delta 1 with respect to that forward path? It will be 1 minus 0 only, because loop gains are 0 and afterwards all the terms will be 0, so it will be 1 only. So now I can finally put this all the values in the final equation. So C by R, right, will be P1 was G only times delta 1, which is 1 only, divided by delta is what, 1 plus GH, right? Here 1 plus GH. Okay, so this becomes G by 1 plus GH. Okay, G by 1 plus GH. So we know already answer to this question, so it may seem like, why am I doing this so slowly, and like this is taking so much time. We can do this just in a matter of seconds from the previous methods, right? Yeah, so this was just to show you and how to calculate this. So this is another example. Okay, this is another example. We will do this in the next class, because this class has already gone too long. So these are few examples that I wanted to do in home. Okay, solve this using SFG. This we have already done previously. Okay, but now solve this using SFG and cross verify whether you are getting the correct answer or not. I will solve many of these questions in the next class, so this class will not extend. So just take the screenshot and solve all of this question. Okay, solve the transfer functions using SFG. This is another one. This is also a gate question. Okay, and we have another question. Yeah, this is also another gate question. Take the screenshot and solve them. Okay, this is also another gate question, right? I think we are done. Yeah, we are done. Okay, so next in next class I will give you, like, I'll solve this question and more few questions. So let us get a quick recap of what we did in this lecture, right? So firstly, we learned like what is SFG. SFG is basically a graphical representation of the block diagram. Block diagram is also a graphical representation of the whole system, right? To understand it in a more easier manner, analyze it in a more easier manner, but to further simplify and to analyze it and calculate the whole transfer function, right? Calculating the transfer function from block diagram may become tedious sometimes. Why you like, as you saw, right, as I was solving that question at the start of this lecture, it was becoming tedious. So using SFG, we have a particular formula. If you use that formula, and we'll get our transfer function, right? So that's why it becomes a bit easier. Okay, so yeah, these points have we already understood. Okay, one thing to remember is that nodes are used to represent variables. How? I will show you. Okay, or here or in the state space chapter. Okay, any chapter I will show you what do you mean by this particular sentence. Normally the nodes are arranged from left to right, the flow is from left to right, input to output. Okay, that is what we know. Okay, signals travel along branches. Okay, along branches, as I explained to you, only in the direction described by the arrows describe the direction and the flow, right? And they travel along the branches, okay, between two nodes. And this is our Mason's gain formula. This may seem a bit like too much for you, at first to remember, but once you like get used to it and do enough sums of that question, right, of this particular type, then this will automatically get into your head. This will automatically, you will remember. Okay, we will do many questions from there. You will understand, yeah, this is not that difficult as you thought previously, right? So yeah, this is what Mason's gain formula is. So I defined what is input node, what is output node. Like input node, everything will come into that node. Output node, everything will go out from that node. Okay, sorry, I talked opposite. Input node, everything will go out from the node. Input, we're giving the input and everything will go out from the node. And output node, everything will come into the node and we're taking the output from there. Okay, so that is the important point for input and output node. But the key point is, a non-output node can be converted into simply output node because there is no loading effect, right? I can simply take output from any of the nodes. But if I give the input to the node, then the overall system will get disturbed. Okay, the ratio of C by R will get disturbed. So I can just simply give input to any node and calculate that, right? So that is difficult. So just keep that in mind. Okay, I can't give input to any nodes. Okay, so yeah, that is what I explained. Then I explained what is the forward path, what is determinant of the SFG, what is the formula for that. Then I explained associated path factor, all those things. Okay, we did. What are the rules of flow, when to take notes, how to like should we take notes or not. Okay, we should always take individual loops notes, because that is the safer bet, right? If you can't make a mistake in that. Okay, if you just combine these, right, then that may cause some mistake in you, okay, in the question, solving the question. So it's very important to take them as separate. Okay, so yeah, we have multiple summing points. Then we did one example problem. Okay, so in the next class I will see you, and thank you for watching.